Hello my friends and welcome back to the You Can Do TV channel. The Skylum multi-apartment project is delivered through a construction process centered on precision, efficiency, and prefabrication. Structural elements are engineered in advance, allowing key components to be manufactured under controlled factory conditions before arriving on site. Foundations and load-bearing systems are installed according to a strict sequence, ensuring accurate load transfer and long-term stability. Prefabricated wall and floor elements are lifted into position, reducing on-site labor and shortening construction timelines. This method improves build quality, minimizes weather-related delays, and limits disruption to the surrounding urban environment. Through coordinated planning, modern construction technologies, and disciplined execution, the Skylum project demonstrates how contemporary residential buildings can be realized faster, cleaner, and with consistently high structural performance. In Leeds, emerging Air Park district, construction is advancing with the installation of prefabricated brick facade systems for 2 commercial and office buildings. Fully finished facade panels are manufactured under controlled factory conditions in Lithuania, where brickwork, insulation, and structural connections are integrated before transport. Delivered directly to site, the elements are lifted into position and fixed with high precision, significantly reducing on-site labor and weather dependency. This method ensures consistent quality, tight tolerances, and rapid enclosure of the buildings. By shifting complex facade work off-site, the Air Park project achieves faster installation, improved safety, and a clean, efficient construction process suited to a dense urban environment. The Astra Bridge marks a technical breakthrough in managing highway rehabilitation under growing traffic pressure on Switzerland's national roads. As daytime and nighttime traffic volumes continue to increase, conventional lane closures have become both inefficient and hazardous. The Astra Bridge introduces a different construction logic: uninterrupted traffic above, full-scale roadworks below. With a total length of 256 meters, the bridge creates a protected working corridor of over 100 meters beneath a clearance envelope of 3.10 by 5.10 meters. This geometry allows the use of standard milling machines, asphalt pavers, rollers, and dumpers, rather than specialized compact equipment. Above the structure, traffic flows on 2 narrowed lanes with reduced speed, while the typical congestion caused by lane reductions is largely avoided. Installation is a highly coordinated engineering operation carried out over 2 nights. The bridge arrives in 47 heavy load transports with components designed to remain within transport limits. Motorized ramp sections are self-unloading via onboard hydraulic systems, while lighter, non-motorized elements are positioned by crane. Assembly begins with the lower ramp sections, followed by a specially shaped transition element that smooths the interface between roadway and bridge. The upper ramp halves then advance under hydraulic drive, aligning with millimeter precision before being bolted together. After each connection, all control systems are software synchronized into a single operational unit. Once operational, pavement rehabilitation proceeds below under live traffic. The project's conclusion is straightforward: a safer site, longer effective working hours, and a repeatable system ready for future deployments. At Bad Hoeverdorp, the Bibo concrete artwork marks a technically refined solution developed for the realignment of the A9 motorway. Prefabricated by Martin's Prefab beton, the structure replaces conventional bridge concepts with a continuous concrete arch that carries the roadway without expansion joints. By eliminating joint transitions, the design removes one of the most maintenance-intensive elements in road infrastructure, resulting in smoother traffic flow and improved long-term durability. The construction process is centered on prefabrication and precision assembly. All structural elements are produced under controlled factory conditions, ensuring consistent quality, tight tolerances, and a high-grade finish on visible surfaces. On-site, installation is carried out rapidly, without the need for temporary propping or under support. This allows construction to proceed efficiently from ground level, significantly reducing disruption to surrounding traffic and the local environment. The Bibo system enables slender structural forms while maintaining high load-bearing capacity. Its circular, elliptical, or flattened arch geometries can be adapted to a wide range of site constraints, offering engineers and designers flexibility without compromising structural performance. The arch shape efficiently distributes loads into the foundations, minimizing material use while achieving an elegant and distinctive appearance. Another key technical advantage lies in life cycle performance. Because the road surface spans continuously over the concrete arch, future resurfacing or renovation of the pavement can be carried out without damaging the underlying structure. Production, delivery, and installation are managed as a single integrated process, reducing interfaces and construction risk. At Bad Hoeverdorp, the Bibo concrete arch demonstrates how prefabricated engineering can deliver faster installation, reduced maintenance, and architectural clarity, transforming a functional road crossing into a durable and visually striking piece of infrastructure. The bridge launch in St. Augustin demonstrates the precision required when major infrastructure is built alongside live rail systems. Constructed next to a double-track urban light rail corridor, the bridge was designed to be shifted seamlessly into its final position, an operation demanding exact coordination. Extensive preparatory works set the stage. Existing tracks and embankments were removed. A deep construction pit was excavated, and board piles were installed to form the foundations. The new bridge structure measures 35 meters in length, 15 meters in width, and 7 meters in height, with a total weight of approximately 200 tons. The insertion itself relied on 16 synchronized hydraulic jacks, pushing the bridge 23 meters along steel girders lined with Teflon sliding plates. The massive structure advanced smoothly and almost silently, guided into position and lowered with millimeter accuracy. Rising across the eastern Bosphorus Strait, the cable-stayed bridge linking Vladivostok to Russky Island was conceived as a strategic infrastructure project under a federal program to develop the Far East as a center of Asia-Pacific cooperation. Beyond its symbolic role, the bridge forms a critical transport artery, integrating island and mainland networks into the broader Primorsky region system. Construction began in September 2008 and advanced under some of the harshest environmental conditions faced by modern bridge builders. Wind speeds reached 36 meters per second, storm waves rose up to 6 meters, and winter ice thickness approached 70 centimeters. Seasonal temperatures ranged from below -30 degrees Celsius in winter to plus 37 degrees Celsius in summer, demanding meticulous planning, robust equipment, and strict process control. To support continuous operations, 2 fully equipped production bases were established on the Nazimov Peninsula and Russky Island. Each facility included reinforcement welding shops, testing laboratories, high-capacity concrete batching plants, mechanical workshops, equipment maintenance units, offices, living quarters, and canteens. New railway lines totaling more than 1.3 kilometers were built, and over 4.5 kilometers of existing track were upgraded to ensure uninterrupted material delivery. More than 320 units of specialized machinery were mobilized, including tower cranes capable of telescoping to 340 meters and heavy lift cranes exceeding 1,000 tons in capacity. Access viaducts exceeding 900 meters in total length were constructed to connect the bridge approaches. Their piers, ranging from 9 to 30 meters in height, support composite steel concrete spans, formed by inclined steel box sections topped with cast-in-place reinforced concrete slabs. The most demanding substructures were the main load transfer piers and pylons, approximately 35 meters high, designed to absorb horizontal forces from the stay cable system and the stiffening girder. Foundation works marked a milestone in Russian bridge construction. Drilling and pile concreting were carried out from floating platforms in water depths of up to 20 meters. Each pylon foundation was supported by 120 drilled piles, 2 meters in diameter, extending as deep as 77 meters. Temporary steel islands and rock-filled artificial peninsulas were created to protect foundations against vessel impact, ice drift, and wave action. Pylon construction employed self-climbing formwork systems, allowing multiple operations, reinforcement, concreting, curing, and finishing, to proceed simultaneously across 7 working levels. This approach significantly reduced construction time, while maintaining strict quality standards across more than 20,000 cubic meters of concrete per pylon. The central span is stiffened by an all-steel box girder extending 220 meters, assembled from 103 prefabricated panels. Delivered by barge and lifted to a height of 76 meters using satellite-guided positioning, the panels were pre-assembled onshore to minimize high-altitude operations in strong winds. Over 30 kilometers of welded joints were completed with 100% ultrasonic inspection. The stay cable system, totaling more than 54 kilometers in length and weighing 720 tons, features compact, high-density strand arrangements that reduce wind load and material consumption while ensuring a design service life exceeding 100 years. Together, these systems define a structure engineered not only for scale, but for durability, resilience, and long-term performance. An enduring landmark for Vladivostok and a benchmark in cable-stayed bridge construction. The Yusufeli Dam, constructed by the General Directorate of State Hydraulic Works within the scope of the Koru Basin project, is set to become the tallest dam in Turkey upon completion. Built on the Koru River in Artvin's Yusufeli district, the project stands out for both its extreme height and its highly unconventional construction methods. The dam site lies within the rugged terrain of the eastern Black Sea region, where steep slopes, deep valleys, and limited access routes create exceptional logistical challenges. To overcome these constraints, heavy construction machinery is transported using a specially installed cable crane system, similar to the method previously applied at the Ermanek Dam. This system spans a distance of 552 meters between two opposing valley slopes, enabling equipment to be lifted and positioned precisely in otherwise inaccessible areas. The KCS consists of two operational lines. In single-line mode, the system is capable of carrying loads of up to 28 tons. When both lines operate simultaneously, lifting capacity increases to 48 tons. This highly coordinated system allows excavators, drilling rigs, and other heavy machines to be deployed safely and efficiently, ensuring uninterrupted progress despite the site's extreme topography. The synchronized movement of machinery across the valley highlights the advanced engineering and logistical planning behind the Yusufeli Dam project. Known as the Green Ants for their speed and tracked mobility, the machinery fleets of the General Directorate of State Hydraulic Works operate continuously across Turkey to ensure public safety before, during, and after flood events. Deployed from 26 regional machine parks, these units play a critical technical role in flood risk management. Prior to flooding, construction equipment is used for riverbed regulation works, including channel widening, realignment, embankment construction, stone revetment, and systematic cleaning of waterways to improve hydraulic capacity. During flood events, rapid response operations focus on preventing blockages at bridges and culverts by removing large debris such as tree trunks, boulders, and sediment that intensify destructive flow forces. Obstructed structures are cleared to restore safe water passage and stabilize flow conditions. After flooding, machinery is mobilized for damage mitigation, sediment removal, and restoration of river channels. Under Facade coordination, DSIE equipment and operators also support search and rescue activities, ensuring an integrated emergency response through precise, ground-based engineering operations. The T30 Hotel in Hunan Province stands as a defining demonstration of what industrialized construction can achieve at scale. Delivered by Broad Sustainable Building in just 360 hours, the 30-story structure was assembled using a fully prefabricated system engineered for speed, strength, and efficiency. Structural modules were manufactured off-site with millimeter precision, then transported and assembled in a tightly controlled sequence, reducing construction waste to just 1%. At the core of the building's resilience is a unique diagonal steel bracing system, designed to dissipate seismic energy and deliver earthquake resistance rated up to 9 on the Richter scale, 5 times higher than conventional buildings. The envelope is equally advanced. A 15-centimeter insulated glass curtain wall, combined with 4-pane windows, external solar shading, and internal window insulation, dramatically reduces thermal losses and solar gain. Energy performance is further enhanced through integrated heat recovery fresh air systems. Air entering the building passes through a 3-stage filtration process, delivering indoor air that is up to 20 times cleaner than typical urban environments. This system maintains continuous ventilation without sacrificing energy efficiency, resulting in overall performance 5 times more efficient than traditional construction. The T30 Hotel is more than a record-breaking project. It represents a scalable model for resilient, low-waste, high-performance urban buildings, defining Broad's vision for sustainable city living. At Broad Town, the F-Tower redefines high-tech construction. Built entirely from stainless steel using ultralight B-core slabs, the building was factory-made and assembled at 3 floors per day. Stronger than steel, earthquake-resistant, and dramatically cantilevered, it proves buildings can be engineered miracles. At Ravinga's City Space, homes take shape through a streamlined prefabrication process developed by in-house. Wall elements are manufactured in a controlled factory environment and transported directly to the construction site, where installation becomes a precise assembly operation rather than traditional on-site building. This approach allows work to progress at nearly double the speed while maintaining consistently high quality. Factory production minimizes material waste, reduces noise, and significantly lowers environmental impact in surrounding areas. By shifting critical construction stages off-site, modern technologies enable greater efficiency, cleaner workflows, and predictable results. At Ravinga's City Space, prefabrication is not just about speed. It is about building durable, well-crafted homes through smarter, more responsible construction methods. Construction of the secondary school in Mallow, County Cork is progressing through a carefully sequenced structural phase. A key operation on site is the installation of precast concrete wall panels, manufactured off-site under controlled factory conditions. Panels arrive ready for placement, complete with cast-in connections and lifting points. Using mobile cranes, each element is lifted into position, aligned to survey control points, and temporarily braced to ensure stability. Once set, connections are completed and tolerances checked before moving to the next panel. This method allows rapid enclosure of the building, reduces on-site labor, and ensures consistent quality. By combining prefabrication with precise on-site assembly, the project maintains high construction efficiency while delivering a durable, robust educational facility. Sculpting Palm Jebel Ali in Dubai is a landmark exercise in large-scale marine engineering. The project is shaping a palm-shaped archipelago with 16 fronds, a 6-kilometer trunk, and more than 60 kilometers of new beachfront. Since 2024, dredging and reclamation works have focused on forming stable foundations for future villas, hotels, and recreational areas. Sand is reclaimed from offshore borrow areas using trailing suction hopper dredgers, then placed in controlled stockpiles and redistributed by dump trucks. Surface and deep compaction, including stone columns and vibroflotation, are carried out in parallel to ensure ground stability, with dredging fleets, earth-moving equipment, and construction crews operating simultaneously. Dredging lies at the technical core of Jan de Nul Group's global operations, representing a discipline where engineering, precision, and scale converge. At its essence, dredging is the controlled removal, transport, and placement of sediment to reshape coastlines, deepen waterways, and create entirely new land. Each project begins with detailed seabed surveys and soil investigations, allowing engineers to select the appropriate dredging method and equipment for the material and conditions involved. Modern dredging integrates powerful cutter suction and trailing suction hopper dredgers, capable of operating continuously in open seas, rivers, and confined ports. Material is excavated, hydraulically transported, and accurately placed, often within tight tolerances that directly affect long-term stability and navigability. Equally critical is sediment management, where grain size, moisture content, and compaction are carefully controlled to ensure structural integrity, especially in land reclamation works. Beyond excavation, dredging systems incorporate environmental monitoring, turbidity control, and adaptive working windows to limit ecological impact. Through this combination of heavy machinery, data-driven planning, and marine expertise, dredging becomes not just earth-moving, but a highly engineered process that supports global trade, coastal protection, and urban expansion. At its modern facility in County Meath, Keegan Precast operates a tightly integrated manufacturing process, where digital engineering flows seamlessly into automated production. The focus is on twin wall panels and filigree floor slabs, precision-built elements designed for speed, accuracy, and structural performance on site. Production starts at the plotting station, where each steel pallet is automatically marked with panel geometry, openings, and service penetrations. Magnetic shutters are cleaned, positioned, and sealed to achieve tight tolerances along panel edges. Electrical boxes, conduits, and embedded items are fixed in place before release oil is applied. Reinforcement cover spacers follow, preparing the pallet for steel placement. At the robotic steel station, reinforcement is cut, bent, and positioned directly from coils, guided by the digital model. Hidden beam links, connectors, and lattice girders are added with machine-level accuracy. Insulation panels fitted with carbon fiber wall ties are measured and staged, while plastic-coated spacers ensure consistent separation between the two concrete skins. Concrete production is fully automated and carried out on site using EN 206 certified batching systems. Aggregates are sourced and processed internally, ensuring consistent quality. High-strength concrete is evenly spread, compacted on oscillating platforms, and cured in a computer-controlled chamber capable of managing dozens of pallets simultaneously. The second skin follows the same process before the first skin is inverted by a rotating crane and precisely joined in fresh concrete. After final curing, panels are demolded on tilting tables to prevent damage, transferred to custom transport stillages, and prepared for delivery. From digital design to finished product, Keegan Precast's twin wall and floor systems demonstrate how automation, engineering discipline, and material control converge to deliver reliable, high-performance precast construction. The Maxtruder Foundation Pile Formwork system defines a highly structured and repeatable production process within the precast concrete factory. Manufacturing begins with the configuration of the modular formwork, selected according to the required pile cross-section and length. Reinforcement is prepared and positioned with precision before concrete placement, ensuring consistent structural performance across every unit. Concrete is then introduced into the Maxtruder formwork under controlled conditions, allowing for uniform compaction and surface finish. Because curing takes place entirely in the factory, strength development is predictable and independent of weather. Once curing is complete, piles are demolded, inspected, and prepared for transport, with their full load-bearing capacity already achieved. From factory casting to final placement, the Maxtruder system delivers a continuous, efficient foundation workflow built around precision and reliability. Pile driving is a fundamental construction process used to create deep, reliable foundations for buildings, bridges, and heavy infrastructure. The operation begins by positioning a pile, typically a long concrete, steel, or timber element, at a precisely surveyed location. A pile driver then applies repeated energy at the pile head, forcing it downward and transferring load through weak surface soils to stronger layers below. As the pile penetrates the ground, surrounding soil is displaced and compacted, increasing bearing capacity. Driving continues until a specified depth or resistance is reached, confirming that the pile can safely support design loads. Different driving systems are selected based on ground conditions and pile type. Diesel and hydraulic hammers deliver high-impact energy, while vibratory drivers use controlled vibration to reduce soil resistance during penetration. Though demanding and highly regulated, pile driving remains essential for long-term structural stability and performance. Construction of Strandpavilljoen Reuring on the city beach of Hoorn begins with a carefully engineered foundation process adapted to reclaimed ground conditions. The pavilion is built on hydraulically filled sand, where a dense upper layer requires pre-drilling before pile installation. Prefabricated concrete piles are then installed to transfer loads to stable soil layers below. Once piles are cut to level, precast beams are installed to form a rigid load-bearing grid. Prefabricated floor elements and stair units follow, allowing rapid assembly with consistent quality. The superstructure, composed of steel, timber, and concrete, is erected on this prepared foundation platform through controlled sequencing, factory-made components, and site-adapted piling techniques. Reinforced autoclaved aerated concrete load-bearing panels are increasingly applied in commercial construction where speed, structural performance, and energy efficiency are critical. When installed horizontally, these prefabricated wall panels function as primary load-bearing elements, transferring vertical and lateral loads efficiently while maintaining a lightweight structural system. Factory production ensures precise reinforcement placement, dimensional accuracy, and consistent material quality before panels are delivered ready for installation. On site, the panels are lifted into position, aligned, and mechanically connected to the structural frame or adjoining panels, significantly reducing construction time compared to conventional masonry or cast-in-place concrete. Due to AAC's cellular structure, the panels provide excellent thermal insulation, contributing to lower heating and cooling demands, while also delivering high fire resistance and acoustic performance, key requirements for commercial buildings. During erection, panels are lifted into position, aligned, and mechanically connected to adjacent elements or the main structure, allowing rapid enclosure of the building. Compared with traditional masonry or cast-in-place concrete, this approach shortens construction schedules and reduces labor demand. The cellular structure of AAC provides excellent thermal insulation, strong fire resistance, and effective sound attenuation, all of which are essential for commercial environments. The installation phase of the new Asia aluminum formwork system is a highly structured, method-driven operation engineered to achieve speed, precision, and repeatable quality in reinforced concrete construction. The process begins well before materials reach the site through a 5D automatic typesetting system. This digital platform integrates architectural geometry, structural design, quantities, sequencing, and installation logic into a single coordinated model. Every wall panel, kicker plate, tie location, opening, and embedded item is predefined, allowing the on-site workflow to follow a precise and predictable sequence. On-site, preparation starts with checking floor flatness. Any deviation beyond allowable tolerance is corrected to ensure even load transfer and accurate alignment of the formwork. Structural sidelines are then drawn on the slab, marking wall axes, panel boundaries, corners, and service openings. These reference lines govern the entire installation and are critical for maintaining dimensional accuracy and vertical control. The first physical components installed are the kicker plates. Fixed along the wall base using dedicated screws, kicker plates define wall position and elevation while preventing movement during concrete placement. Once secured, all aluminum panels receive a uniform application of mold oil. This treatment reduces adhesion, protects panel surfaces, and ensures clean demolding with a high-quality concrete finish. Installation continues with the incomer wall panels, which serve as primary reference panels. Standard wall panels are connected sequentially using a pin and wedge locking system that creates a rigid, continuous form face. External angle panels are installed at corners to maintain sharp geometry and structural continuity. Each connection is inspected to confirm tight engagement and proper load transfer capability. Wall ties are then installed at predefined spacing to control wall thickness and resist fresh concrete pressure. PVC sleeves are fitted over the ties, preventing bonding and allowing for later removal without damaging the concrete. Reinforcement bars are installed inside the formwork in strict accordance with structural drawings, ensuring correct cover, spacing, and anchorage. At this stage, embedded components such as electrical socket boxes, switch boxes, conduits, and sleeves are accurately positioned, eliminating the need for post-cast cutting or drilling. Once reinforcement and embedded items are complete, the remaining wall panels are installed to fully enclose the vertical formwork. Attention then shifts to horizontal elements. Soffit panels and beam panels are installed adjacent to support beams, forming the underside of beams and slabs. Floor corner panels are placed to ensure clean intersections between walls, beams, and slabs. Slab panels are then installed across the floor area, supported by the cartridge system and adjacent formwork components. A double-track confirmation process follows, during which alignment, elevation, and locking integrity are thoroughly checked. Staircase formwork, often pre-assembled, is installed next, allowing complex stair geometry to be formed with high-dimensional accuracy. Ceiling light boxes and additional embedded fixtures are fixed in position to ensure precise alignment with architectural finishes. Before concrete placement, installation hooks and sinking plates are fitted where required. A comprehensive inspection verifies panel alignment, wall tie installation, reinforcement positioning, and embed accuracy. All formwork surfaces are cleaned, and mold oil is reapplied as needed. Concrete pouring is carried out in a controlled sequence to manage pressure on the aluminum panels and maintain stability. After sufficient curing, dismantling begins systematically. Wall panels are removed first, followed by wall ties and PVC sleeves using specialized pullers. Tie holes are sealed and surface touch-ups are performed to achieve a uniform finish. Final measurements of flatness and verticality confirm compliance with design tolerances, demonstrating the technical efficiency, repeatability, and high construction quality delivered by the new Asia aluminum formwork installation process. The Rectolite prestressed ribbed floor system represents a modern alternative to conventional beam and block concrete slabs, combining structural efficiency with fast, lightweight installation. The system is based on prestressed RS floor beams, working together with ultralight infill elements made from high-strength pressed wood. This configuration significantly reduces self-weight while maintaining load-bearing performance, making Rectolite suitable for new residential buildings, public facilities, and floor replacement projects in older masonry structures. Once the beams are aligned and leveled, the lightweight Rectolite infill blocks are placed between them. One pallet of infill material is sufficient to cover up to 90 square meters of floor area, significantly reducing transport and handling costs. The infill elements are easy to cut and shape, allowing precise openings for staircases, ducts, and service penetrations without specialized tools. This flexibility makes the system highly adaptable to complex layouts and renovation constraints. After infill placement, system cover elements are installed where required, and a reinforcement mesh is laid across the entire slab surface. Additional reinforcement bars are placed in support zones to manage negative moments and ensure structural continuity. The minimum thickness of the concrete topping is 4 centimeters, forming a composite slab once cast. Concrete placement completes the structural action, locking the prestressed beams, infill, and reinforcement into a single load-bearing system. For maximum spans of 8.5 meters, only 2 assembly props are required, simplifying site logistics and accelerating progress. After curing, the supports are removed, leaving a flat soffit suitable for suspended ceilings. Adjustable hangers allow easy installation of services, while the reduced slab depth provides space to conceal mechanical and electrical installations. With fire resistance ratings up to REI 60, rapid installation, low weight, and high adaptability, the Rectolite system delivers a technically efficient floor solution that doubles installation speed while meeting modern structural and functional demands. Cement is an essential part of modern life and the foundation of concrete, the second most widely used material in the world after water. Its production begins with selecting a factory location close to a limestone quarry, since limestone is the primary raw material and proximity reduces transportation demands. Mining operations extract limestone rock through controlled blasting, after which the material is hauled to crushers and reduced to smaller fragments. The crushed limestone is stacked and homogenized to ensure consistent quality. Clay and iron ore are then added in precise proportions. These materials are fed into mills, where they are ground into a fine powder known as raw meal. This uniform mixture is stored in silos before entering the next critical stage. The raw meal is preheated in a cyclone tower and then fed into a rotary kiln, where temperatures can reach up to 2,000 degrees Celsius. Under these extreme conditions, the material transforms into clinker, the fundamental component of cement. Continuous operation of the kiln is essential for maintaining product quality. To reduce carbon emissions, alternative fuels such as processed waste, tires, and industrial residues are increasingly used alongside petroleum coke. After leaving the kiln, clinker is rapidly cooled from over 1,000 degrees Celsius to about 100 degrees, a step that directly influences its final quality. The cooled clinker is stored in silos before being ground with gypsum and other mineral additions, such as blast furnace slag or pozzolana, to produce different cement types. The finished cement is stored, packaged, or delivered in bulk, all under constant monitoring from a central control room, the operational heart of the plant. Concrete pumping is a fundamental process in modern construction, enabling the controlled and continuous placement of concrete exactly where it is needed. The operation begins with a carefully designed concrete mix, optimized for pumpability while maintaining strength and durability. The concrete is fed into the pump hopper, where hydraulic pistons generate the pressure required to move the material through a system of steel pipes and flexible hoses. Depending on project requirements, either stationary pumps or truck-mounted boom pumps are used. Stationary pumps are suited for long horizontal distances or confined sites, while boom pumps provide vertical reach and precise placement through articulated arms. Throughout the pumping process, flow rate and pressure are closely monitored to prevent segregation and ensure a uniform mix reaches the point of placement. At the discharge point, concrete is evenly distributed into formwork or onto slabs, and immediately compacted using vibration equipment to remove entrapped air and achieve full consolidation around reinforcement. Concrete pumping significantly reduces manual handling, shortens placement time, and improves site safety. Its efficiency and accuracy make it the preferred method for foundations, walls, slabs, and high-rise structures. At Parkline in Veghel, the Cutter soil mix solution demonstrates how ground engineering can combine precision, strength, and water control in a single integrated system. The Cutter soil mix process is built around a powerful cutter head equipped with 2 counter-rotating wheels. Between these wheels, a cement slurry is injected directly into the soil, creating a homogeneous soil-cement mixture. Under its own weight, the cutter head penetrates the ground smoothly, forming a continuous and highly controlled CSM panel. Technically, the cutter system significantly improves soil mixing efficiency and uniformity. For the first time, the cutter soil mix wall functions not only as a temporary support, but as a fully structural, soil-retaining and water-retaining wall. Its high water tightness makes it especially effective compared to traditional sheet pile cofferdams, substantially reducing groundwater flow. When natural water-inhibiting layers are absent or deep, the system can be enhanced with injected sealing layers or selective reinforcement, keeping solutions both flexible and economical. Once a panel is mixed, reinforcement can be introduced immediately. Depending on structural requirements, steel IPE beams, reinforcement cages, or steel nets are lowered into the fresh CSM column, sinking naturally into the mixed mass. Construction follows a carefully sequenced pattern. Odd-numbered panels are installed first, allowed to harden for approximately 1 day, and then intermediate panels are cut. This method ensures consistent quality and long-term stability of the surrounding soil. The resulting wall is moderately smooth, space-saving, and structurally versatile. It can carry horizontal and vertical loads, reduce demands on permanent basement walls, and even remain visible as a finished structural element. With modern cutter soil mix equipment, Bodenbau delivers complete engineering, planning, and execution, focused on safety, environmental care, and durable underground construction. On a demanding foundation site, the PC400 excavator demonstrates controlled power while cropping 350mm precast concrete piles under a regulated 4-bar hydraulic setup. What was once a slow, labor-intensive, and physically punishing task has been transformed into a precise mechanical operation. Equipped with an Australian pile cropper's attachment, the excavator applies uniform pressure around the pile circumference, inducing a clean, controlled break exactly at the designed cutoff level. The process eliminates the need for jackhammers, cutting torches, or manual chiseling, significantly reducing noise, vibration, and operator fatigue. Each pile is cropped in a matter of minutes, producing a level, undamaged surface ready for immediate structural integration. The reinforcement remains intact and exposed to the correct height, ensuring full compliance with structural specifications. From an engineering standpoint, the advantage lies in consistency. Every pile is treated the same way, regardless of site conditions or pile density. For crews on the ground, the benefit is equally clear: safer working conditions and faster production rates. With hydraulic precision replacing brute force, painful piles truly become a thing of the past. Next Trencher Barcelona introduces a new generation of trenching machines shaped by more than 30 years of field experience. Designed, manufactured, and refined through real-world operation, these trenchers are engineered for precision excavation in demanding ground conditions. The base models cut trench widths ranging from 12 to 150 centimeters and reach depths of up to 5.5 meters, even in hard, abrasive, and high-resistant soils. This depth of experience is evident in every technical detail, from reinforced cutting systems to optimized power transmission and wear-resistant components. Next Trencher machines are built to maintain stable cutting performance across varying terrain types, including rocky substrates where conventional trenchers struggle. By combining robust mechanical design with adaptable configurations, the Next Trencher range delivers reliable, controlled trench excavation for infrastructure, utilities, and industrial projects, offering contractors a versatile and efficient solution backed by decades of trenching expertise. Driven piles are installed deep into the ground to provide a stable foundation, transferring structural loads to competent soil layers and ensuring long-term stability of the units under high operating pressures and vibrations. These systems remove moisture, regulate pressure, and ensure stable, safe, and efficient downstream processing for petrochemical production and distribution.